So first, questions about any of the homework? Okay, today's is going to be on, we're going to cover a number of things today. We're going to start off talking about a quick step function review. And then we'll talk about graphical convolution. We brought it up before, but today's lesson you'll actually end up feeling comfortable with it. And last, we'll talk about transfer functions. And if we get time, I'd really like to do an example that shows how you can use this mathematics in areas completely outside of electrical engineering to analyze, say, mechanical systems. Let's begin with a review of step functions. So a step function, you already know, looks like that. 0 pops up to 1. An alternate way to describe it is piecewise linear, where we say it's 0 for time less than 0 and 1 for time greater than or equal to 0. And what happens exactly at 0, we really don't care about. Then you can start to do tricks with them. And again, we don't care what it does exactly at 0, because what it does at a moment in time, as long as it's a finite height, it has 0 energy. And so if it has 0 energy, it cannot affect anything in the world. So let's take a look at what u of t minus 3 is. So the deal with u of t is that it always kicks, it always changes when the argument is 0. So to make the argument here 0, we need to have t equals 3. And then the way that I evaluate what's going on is I just give myself a very large value of t, like infinity. And for infinity, you can see this will be like infinity, like a million. And so you can see u of a very large number minus 3 is still going to be a very large number, which will be greater than 0. So for large numbers, it's high, and for small numbers, it's low. So that's one type of u of t's. But what happens if our argument is negative? So now we've got a negative t. And so, Joe, what does that do? U of negative t.
That would be 1 for all values less than 0.
That's it exactly. Yeah. So it still kicks on. It still kicks on when the argument is 0, which happens at t equals 0. But the difference, as Joe said now, is that if you give it a really negative argument, negative big number, a negative big number is a positive number. And since a positive number is greater than 0, the u of t is going to be 1 for this region and 0 over here. And you can play that game too about delaying things by a certain amount. So a u of, say, 3 minus t, where does that kick on, Preston?
T equals 3.
That's right. And by the same reasoning, since we've got a negative t argument, it's high for time less than 3 and low for time greater than 3. If you put in an argument of 4 here, you can see 3 minus 4 is -1, and u of -1 is definitely 0. Okay. So let's take a look at other forms. I'm sorry, I've got got a call coming in. So you can add steps together to make things. You can take a u of t function, which we already said looks like this, and you can add it to, say, a u of 3 minus t, which we already described above, looks like this. And then what does that result look like? So what does the top plus the middle look like, Dom?
I'm sorry, sir. I was trying to tell my roommate to be quiet. What was the question?
Yeah, I'm trying to tell the tailor shop who's calling me to be quiet too. My question is that if you've got u of t here, and if you add it to u of 3 minus t, what do you get as a result?
It's going to be 1 from 0 for time less than 0, and then for time greater than 0, it will be 2.
It'll be 1 for time less than 0. That's right. Since we're adding 0
not multiplying
to
right?
1. For this particular one, I'm adding.
Okay, so then it's going to be 2, or do you count that as 2? So it's up.
1 plus 1 is 2.
So then it goes to 2 until whenever the top one is at 2. I think that's at t equals 3.
That's right.
And then it goes down to 0. 1.
Back to 1, 2, 1. Okay, good. So you can graph various things, and if we wanted to make this a top hat that started off, and if we wanted to instead do an extra step to create this kind of waveform, how could we modify our u of t plus u of 3 minus t? Let's see, Aiden?
I'm sorry, sir, I missed that.
Yeah,
How could you?
let me switch over to the same color I've been using so far. If you wanted to create a top hat that was 0 up until 0, popped up to 2 until time equals 3, and then went back to 0, that's almost the same thing as what we've got to the left, but it's not quite. What we have to the left, we said, is u of t plus u of 3 minus t. So how can we modify that to make it just simply this? What can we add or subtract to this waveform to bring it back down so that it's 0 for most of its life, except between 0 or 3, where it's 1. We'll make it simpler yet. How do we get this?
Can you
pulse?
just subtract 1?
Yeah, that's all. Yep. And then what would happen if you, just continuing it on, if you wanted to make it 2 instead? What could you do to this whole thing?
Yeah, you'd have to multiply the whole thing by 2.
Yeah. So you can do a lot of interesting tricks with U of T's. And we're going to need all those tricks when we do the next step, which is graphical convolution. Okay, this is hard. I don't recall, have we talked about graphical convolution so far?
We went over it, but not in depth.
Yeah, I think, right. I think we did a few lessons ago, and I think people found it confusing, and it is tricky. Graphical convolution is the integral of x of tau, we just need a dummy variable in there, times h of t minus tau d tau. So when I first saw this as an undergraduate, I was confused because there were two variables. There was a t variable and a tau variable, and I wasn't quite sure how to manage all that. So what this is saying is that for any particular value of t, to find out what y at 0 is, you're going to have to do this entire integral. And then to find out what y of 1 is, you're going to have to do a whole nother integral, replacing this t with 1. And to find out what y of 1/2 is, or what y of 7 is, or what y of -4 is, each one's going to require a separate integral. So that's the way to interpret this equation. And the way to find it is you're going to first plot this part. And you'll notice that's not a function of t. We want to find, the only way to solve this graphically is to graphically find areas for t equals 0, for t equals 1, for t equals 2, for t equals 3, and to keep moving t around, keep shifting it like that. But for each of these different values of t, our x of tau doesn't change. But this next one does. And so underneath our x of tau, you're going to plot this. And graphical convolution is sometimes called the flip and shift method, because if we start off at t equals 0, then what we're left with is just flipping our h. If we start off at t equals 0, we're plotting h of negative tau, which is just the flip version of h of tau. And then we're going to still evaluate everything at t equals 0. So we're going to multiply the left times the right. And then we're going to integrate it. We're going to find the area of the plot. And that area of the plot equals y at t equals 0. Then we're going to do the whole thing again. Now we're going to, still don't need to replot x of tau because that's the same. Now we're going to shift h to the right. You know, you're flipped h to the right by t. You know, it's to the right for t greater than 0, or you could shift it to the left for t less than 0. And then everything else is the same. You'll multiply, and the area of the plot in general is y of t for your shift of t. And that'll get all your right points, and then to find your left points, it's going to be the same, but you're going to shift it left. And then everything else is the same. Okay. So I'm going to show this instead of, this takes a long time to draw because I'm constantly, for every part of y, I'm constantly redrawing. For every different t, I'm constantly redrawing this h of t minus tau. So rather than take all this time to draw it myself, I wrote a program that will do it. And here it is. So it's in MATLAB. And I'll make it available to you if you're interested. So what we have here is our x of t. I'm going to have two pulses here. So what we have here is our x of t in blue, and our h of t is in red. So this is what x of t looks like in blue. It's a pulse between 0 and 1. It's a height of 1, and our h of t is in red. Same exact thing. So our first step that we do is to take h of t and to flip it left and right, flip it right around that 0 axis. So instead of it being like the old blue one, now it looks like this flipped red, it shifted. And when we multiply our red and our blue waveforms together, we get this waveform in the middle, which is 0 everywhere. And that's why in this bottom waveform, which is y of t, we're only calculating it for a 0 shift. So we're only calculating what y of t is, even though y of t is shown entirely, we're really only calculating the green dot here, which shows the area underneath the product of the original x with a flipped h. Thumbs up on that? Okay. And now we're going to shift our and now we're going to shift our h to the right. We can shift it by any amount. I'm going to shift it by 1/2. So when we have it by a half, now we've got our h of t minus tau. So it's going to be 1/2 minus tau for this particular equation. And when we multiply our shifted, flipped h of t in red with our original unchanged x of tau in blue, we get this waveform. 0 pops up, goes down, and the area underneath that, you can see it's 1 high, it's a half wide, so its area is a half, and that's why y of t at t equals 1/2 is also 1/2. And as we shift this thing further to the right, now we've shifted it to the right by 1. We flipped it around, and then we shifted it to the right, and now it looks like its original waveform. Multiply the two together, we get this box of area 1, and so our y of t is 1. And as we continue to shift it more than 1 to the right, if we shift it to 1.5 to the right, now there's only half a width of box after you multiply the two together, and that has an area of 1/2. And so this is going down. You can see that as we continue to shift it to the right, we'll have less and less overlap, less and less area, and y of t gets to be 0. Similarly, if this is t equals 0 right here where we began, if we shift it further to the left, there'll always be no overlap, and so our response will always be 0. So using this graphical method, you should be able to numerically precisely convolve any kind of flat-topped, square-shaped x of t with any kind of flat-topped, square-shaped h of t. Let's take a look at a different kind of waveform. Now maybe our h of t isn't a pulse, but it's a step. So here we flipped our before I go on, are there any questions on this? Do you have any questions on this first demonstration?
So it really doesn't matter where h of t starts as long as it starts before like where the two start intersecting?
It absolutely matters where h of t started. So if h of t originally started out here, if it went up at 1 and went down at 2, then when you flipped it around the 0 point, it would look like this.
Okay, so you always flip it around the 0 point?
You always flip it around the 0 point. Why do you always flip it around the 0 point? Because that convolutional integral says it's the integral of x of tau times h of t minus tau. So if you're going to evaluate that at t equals 0, as we do when we start, then that becomes h of t minus tau, or h of 0 minus tau, which is h of minus tau. And h of minus tau just means take your function h of tau and flip it around the 0 point. Any other questions? Let's do it with a different input let's do it with a different h of t. Let's do it with the step. So now we've got same blue x of tau, and we've got a, in our original thing, before we put it in our integral, we've got the same blue x of t, that's a pulse, 0 to 1, and now we've got a red step, x of h of t. Our first step is to change them from functions of t to functions of tau, and to flip our h of tau around. So this is our h of minus tau. And this is going to give us the product of the blue with the red at 0 will give us our answer of y of 0. So when we multiply the two together, it shows pretty much there's no overlap, and so our result is 0. And then if we want to find out what our y of t equals 1/2 is, we shift our flipped h of t to the right by 1/2. When we multiply it, we've got this 1/2 unit wide by 1/2 unit wide by 1 unit high product, and the area is 1/2. So y of 1/2 is 1/2. And as we move it further over, to find out what our answer is at t equals 1, we have to shift our flipped h of t to the right by 1. We get this red thing. The product is this, a unit box, and so our our y of t equals 1 is also 1. But as we shift our flipped h of t minus tau still more to the right, it doesn't uncover, its product doesn't uncover any more of our box, and so our y of t remains stable at 1. And you can also see why for time less than 0, we get 0 as a result. Although both of these things, the pulse and the step, both started to go up at 0, realize that if they didn't go up at 0, then perhaps our y would not go up at 0 either. That would be shifted as well. So these are things, let's do it when they're both steps. When they're
I had a
both,
quick question.
shoot.
Sorry.
Yeah,
So,
yeah, shoot.
So saying y of 1 would just be saying the system's response to a given impulse at time equals 1.
It would be the system's response to this pulse, not an impulse. But what you're finding, what this is showing here is if your input looks like this pulse that goes between 0 and 1, and is a height of 1 is 0 otherwise, and if your system that you're talking about has this kind of step impulse response, then at time equals 1, your output will be 1.
So why is it called pulse and then versus impulse response? Why wouldn't it be called pulse response if it's a response to that input?
So the impulse, that's a really good question. Everyone listen up to this one because you're going to forget it. The impulse response is what the system's response is to an impulse in. This is not an impulse in, this is a pulse in. Here's an impulse in. If you put an impulse in, then your response is going to be, your y of t down here is going to be the same thing as the system's impulse response. So normally when a response, a y of t, is a signal. It's not a system, it's a signal. This top thing is a signal. All everything on the left here are signal. Everything on the top left is a input signal, x of t. Everything on the bottom right is also a signal. It's a y of t. However, this thing in the lower left is not a signal. This is a system. This is a complete description of a system. This is the verb. This red thing describes how the system changes the input in the upper left to the output in the lower right.
I thought y of t was the relation, like the actual system relating the input to the output.
No, y of t is the output. X of t is the input signal, y of t is the output result, and h of t is the description of the verb that changes that input noun to the output noun. If you've got a circuit, your input voltage is your x of t, up here in blue. The voltage across the output resistor, say, that you're interested in is your output, your y of t. And the circuit itself, those resistors, capacitors, inductors, transistors, everything in the middle, is what's represented by this h of t. That's your actual verb.
Okay, I got it. Thank you.
Yeah, and I'm glad that you've got it. I hope everyone else gets that. It's a really subtle point. It's easy to forget that h of t is a verb. It's the system. It's the thing that changes your input to your output. And for the particular case, for the very particular case, when the input is a impulse like we just did, then the output y of t is your impulse response. Because that's what the impulse response really is. It's the response of the system to an impulse. Let's just see why that's true, by the way. So our impulse in looks like this blue thing, and it goes up to infinity. I can't draw it. And here's our flipped h of t. And we want to find out what our y is at 0. So at y equals 0, for y equals 0, just before 0, for y equals 0 minus, for y equals negative 0.00001, when you multiply these two guys together, it's 0 everywhere, and so a response is 0. But the moment our t is ever so slightly greater than 0, we're multiplying a finite 1 with this infinitely tall impulse, and we get the infinitely tall impulse times 1. But this impulse has an area of, let's hear it, Phil. What's the area of this impulse? 1. And so when we integrate it, it pops up to 1. And as we shift further and further to our right to find out what y of t greater than 0 is, we don't change the product of 1 with this impulse, and it still has an area of 1, so it stays the same. If we put this impulse into a completely different circuit, maybe it had something that looked like a decaying exponential. That's pretty weird. You can see that for time, the output at time just less than 0, there's no overlap. So for any time less than 0, our output will be 0. But the moment that our time is slightly greater than 0, so remember what we did is we took this impulse, we flipped it around 0 to find our red, and now to find out what our y of, say, t equals 1/2 is we shift it off to the right by 1/2. And now we're still left with this impulse, but its area is this area of 1 times the red scalar of wherever it happens to cross. This looks like a little less than 1/2. And so our output will be a little bit less than 1/2. And as we move it further and further to the right, it should be clear that we're multiplying this area by whatever our shifted h of t minus tau was, a little bit further to the right. And so all we're going to do is just redraw our original h of t. And that's why graphically our impulse response is our response to an impulse in no matter what our h of t is.
Why wouldn't that area be getting smaller? Why wouldn't y of t be getting smaller if you're reducing the amount of, oh wait.
Let's analyze it out here. So at this point over here, we're finding y of, say, t equals 1.75. Right? Here's t equals 1, here's t equals 2. So this is about t equals 1.75. And so we've flipped our h of t around 0, and we've shifted it to the right by 1.75. And now we're going to multiply our input, which is an impulse, by our shifted and flipped h of t minus tau. So if you multiply an impulse that's infinitely high, you'll still get an impulse that's infinitely high. But this had an area of 1. The blue had an area of 1. But now we're multiplying it by an by this number right here in red, which looks to me like it has a value of maybe about 0.1. So therefore, this area will be still an infinitely tall impulse, but with an area of 0.1. Since it was an area, it did have an area of 1. We multiplied it by 0.1, so it's got to have an area of 0.1 now. And the integral of this thing is our y at t equals 1.75. But we know that the integral of an impulse out here is 0. The area of the integral of an impulse, the area of an impulse out here is 0. So the only thing that's left is the area in here, which we just said is equal to 1 times 0.1. So this area has to be 0.1, and that's why it decays away. And as we increase this still further, it'll decay away still more. Does that make sense?
Yes, sir.
Great. And I'll leave this up so you can do different tricks with seeing what it is for different types of impulse, different types of systems. You can integrate, you can convolve a step with a step, and then you can kind of see it just goes on and on up forever. And this is in the time domain, and you can almost see what's going on here in the Laplace domain too. The Laplace transform of a step is 1 over s. The Laplace transform of this impulse response is 1 over s. Multiply them together, you get 1 over s squared. And the inverse transform of a 1 over s squared thing is this ramp that goes on up forever. It's t. So two different. So this is hard, and it's just going to require a lot of practice to get good at. This is actually one of the few things that are a lot easier to do in the discrete domain in digital signal processing than it is in the continuous domain. Anyway, I'll put this. I will put this up on our this demonstration. I will put this demonstration up on our Canvas page. Any other questions on graphical convolution? Okay. Last one, transfer functions. This is really the meat and potatoes of what signals and systems is. A transfer function is an equation that describes the system. When I say system for now, think about it being a circuit in the frequency domain. So we've got a bunch of different ways to describe what a circuit is. One way is the circuit itself. Another way is its impulse response. We feed the circuit an impulse. Whatever we get out, we call that its impulse response. And just with that one waveform, that one h of t, we can now figure out what its response is to any input waveform by convolving. But this is a new way to describe what our system is. Here's our input waveform. I'm going to give it by, I'm going to show you what it is by a simple example. Here's a inductor, a capacitor, and our output. Now that's in the time domain. So we can equally well write this in the frequency domain. Sabine, what is our inductor change into?
Just S.
Yeah, that's right.
Are you referring to the inductor or the voltage source?
The inductor.
Okay.
Yeah, the voltage source, we don't know what it is. So if it was Vn of t in the time domain, it's Vn of s in the frequency domain. And then, Chow, tell me about I'm having trouble arranging the picture of all of you. Chow, can you tell me what the capacitor becomes?
1 over S.
Yeah. Okay. So this is just going to be a voltage divider, right? We can read this right out. Our V out is equal to our, what we're trying to find, over the sum times our input. So that's a voltage divider. But what I want you to see with this is that this is our output signal. This is our input signal. So therefore this has to be our transfer function. This is the verb that relates our output to our input. We can isolate this with just simple algebra. We can say our V out over our V in is going to be equal to 1 over S times S plus 1 over S for this particular circuit. And we don't like these compound fractions, so we'll multiply top and bottom by, who haven't I called on? By John. John, what would we multiply top and bottom to get rid of this compound fraction?
You said John, right?
Yeah.
1, so S over S.
We don't want to multiply by 1 over S, if that's what you said.
No, 1, so S over S.
S over S, yeah, right, exactly. So that gives us 1 over S squared plus 1. And that's such a critical idea about our output over input. Realize that this is the relationship, the ratio for any output and input. This is not what the output is for a particular input. But now this equation somehow perfectly captures everything about our system. There's no difference in writing this polynomial equation or writing this whole circuit. It's the same thing. We've encapsulated that circuit into this ratio of polynomials, such an important concept. We're going to give it its own symbol, its own letter, h of s, which is its transfer function. So realize that H of S it describes the system. I know it sounds like I'm really hammering this point home, but at some point you'll forget. In other words, it describes what the circuit is. It does not describe the input in any domain. It doesn't describe it in the time domain or in the frequency domain. And because it describes the system and is not at all describing the input, it's got to assume some sort of initial conditions. And the initial conditions is it assumes 0 initial conditions. It assumes that the capacitor and the inductor are originally discharged. And that's because if they weren't discharged, the only way they could have an initial condition is if the input made them have an initial condition, and then the system transfer function would be a function of its inputs. Any questions about transfer functions? Ben, how many different ways can you describe a circuit then?
So that should be,
I'll start you off. Ways to describe a circuit.
so that should be 2, right? So like the time domain and then S domain.
Yeah. So one way to describe it is, of course, the actual schematic. That's a cheap one. That's just putting it right back. You've got the schematic of the circuit. But the other one is in the time domain. And what's the time domain description called? Ben, I'm just going to have you finish that up.
Like another name for the time domains.
There's a specific symbol we use to describe the time domain description of a circuit. What is that?
So that would be T.
That would be what?
Don't we have, like, for example, the function like y of y, it's gonna be y of t.
Better not be Y, because that's not the circuit. That's an input. Well, Y is actually the output. X is our input, but what's the circuit part? What's the part that transforms our input to our output? In the time domain, what do we call that? Single letter. Single letter.
So tau. No, not. Wait. So it's.
Yeah, you have to give hindrance received there to your roommate. It's not tau, but it is H of t. It's our impulse response. That's the time domain description of a circuit. But that's okay.
Oh, so I thought you was meant like what I was trying to say with the t within, like, for example, if that function is like y, you're gonna put the t inside a parenthesis. And
well, y of t is
that makes sense.
a y of t is the output, but we're not interested in any signals. We're not interested in an input x of t or output y of t. We're interested in only the verb that changes any input to any output. And so that's our impulse response, h of t. But finish up with what you said before. One is time domain, and the other you said is frequency domain.
Frequencies.
And what's the symbol we use for the frequency domain description of our
So
circuit?
that would be capital H and then sub S.
Yeah, which is called our transfer function. So everyone just realized the bizarreness of this, that for the past many years, we've been talking about schematics. But now I'm telling you that instead of drawing this whole schematic, we could just as well have drawn just instead of our schematic, we could have drawn this, which is, this happens to be cosine of t, u of t, and that is an entirely accurate description and replacement for that whole schematic we just drew with capacitors and inductors. Or we could have equivalently said h of s is equal to 1 over s squared plus 1, a ratio of polynomials, which is also in a completely equivalent description to this. That is mind-blowing. What makes this so powerful is that it doesn't have to be just circuits anymore. This could be anything. This could be a suspension of a car system, which we'll talk about in a couple of minutes. what I want you to see is that here's our input. We put it into our impulse response, and we can find our output. And we've covered how you can find the output directly by convolving the input with the impulse response. But you also know how to take the Laplace transform of the input. That gives you x of s. And the crazy thing is this h of t, which was what you got by hitting it with a hammer. It's the response of your system to an impulse in, happens to have a Laplace transform of h of s, which is what you derive down here without any impulses being involved. H of t has a Laplace transform of h of s. You put this in, and now instead of having to convolve, you can just multiply. And then you can inverse Laplace transform them out. So this is sort of the Rosetta Stone that links everything we've talked about so far in this class all together.
Sir, isn't that just like a very graphical or with arrows way of saying taking, instead of doing it with the integral, doing it with Laplace transforms like how we did like 4 classes ago, right?
Yeah, so you've seen this
Same
before,
exact thing.
but the part that you didn't know 4 classes ago is how to derive this part, which now you know, impulse in gives you h of t, and what you didn't know several classes ago was how to derive this, which is what we just covered over to the left. It's to take your circuit, give it an arbitrary V in that you don't specify, find out its arbitrary V out, and then divide the two over here to find your H. And then the really surprising thing should be that capital H of S is in fact the Laplace transform of your impulse response. So these two completely different ways to characterize your black box are actually completely related using Laplace transforms. There's yet another way that you can completely characterize your black box, which we'll talk about in our next exam block. Realize that you're just before I let you go, and I think our class is coming to an end in a minute, realize that the Laplace transform is the ratio in the frequency domain between the output and the input. If we were to take a different output, if we were to say, instead of taking it across the capacitor, maybe we took it across the inductor, or maybe we're looking at the output as being the current in our system, our H of S would be different. But here's the mind-blowing part too. The denominator of the H of S will always be the same. The only thing that will differ as we're looking at this different parts of the system will be the numerator. The denominator will always be the same. So the denominator down here, this is also sometimes called the characteristic equation, because no matter where the output is taken for your particular system, it will be the same. Okay, we have run out of, am I correct in saying our class is over?
Sir, I think we go to 10:45.
I'm sorry?
I think we go to 10:45, sir.
Oh, fantastic. We've got time for my mechanical engineering example. Yeah, sorry, I've got another, I have another appointment that's occurring at the same time, and they're going to wait. All right.
Sir, I have a quick question.
Shoot.
Just about
Yeah.
what you
This
wrote.
diagram is really important, so ask the questions about it.
Right. So the y of t over there, you said it's equal to x of t, which is not equal to h of t. Is that what that's written?
So h of t is definitely different than x of t.
Right.
X of t is our input.
Right.
H of t is our verb. It's our system.
Right.
And y of t is another signal.
Okay.
And it's equal to our input convolved with our impulse response.
Oh, that's an asterisk. That's what it's supposed to be.
Oh, that's supposed to be an asterisk. Yeah, that's
Okay,
right.
thank you,
All right.
sir.
Yeah, sorry about that. No wonder that was confusing. There we go. That's better. Okay, any other questions about this diagram? Because this is immensely powerful and completely non-obvious. All right, let me give a quick example from mechanical engineering. you are working for a company and it's designing a new electric car. See, I probably am not going to be on the aesthetic design team. And the marketing team wants a suspension analysis. Now they're marketing, so they don't really understand all the engineering mumbo jumbo, but they do want to know, they've got some common questions that don't require an engineering background. They want to know, does it bounce when it hits a curb? You obviously don't want it bouncing up and down a whole lot, but you might want it to bounce a little bit. You wouldn't want it to be totally rigid, right? If you went up a curb, it would be a bad thing if it was a completely rigid response. So if so, at what frequency? So it's one thing if it slowly goes up and slowly goes down over the course of maybe 6 seconds, you wouldn't even notice it. If it goes up and down 10 times a second, you will notice that. And if so, what frequency? And also, how fast does it take to settle out and to stop vibrating? Again, you'd like it to stop relatively quickly. You don't want it to be vibrating for the next 20 minutes. So as an engineer, you can do a free body diagram of this car. You can firstly recognize that if the suspension is relatively the same front and back, left and right, let's just analyze one tire to get the feeling of what's going on. So here's the car body. This is the wheel well that I just drew. And to make the numbers easy, I'm going to draw a Y in the positive direction. And the car body's got, your suspension system's got two parts to it. Has anyone ever heard of can someone tell me what a McPherson strut is composed of? Okay, so this is how the McPherson strut works. You want to have some sort of spring connecting your axle. This is your axle. You want to have some kind of spring connecting your axle to the body, because otherwise, if it didn't have a spring, if it was a rigid connection, every little pebble that your car went over that your wheel went over would cause your whole car body to rise up and down. So you want a spring to soften that impact. But if you just had a spring, can you imagine how awful that ride would be? You'd go over a little bump, and your wheel would go up and down, but that would be transmitted to your body through the spring. And now your spring would just bounce up and down and up and down and up and down forever. And it would be really uncomfortable. And so instead, you add to that something called a dash pot. And that dash pot is physically what it is a piston, just like it's drawn. Here's your long piston inside there. And this is the part of the piston that goes up to the car body. This is the part of the piston that's anchored to the wheel, and it's filled with an oil. And there's a tiny little hole that is drilled in there that goes through. And so the oil can go through that hole and up. If you push the piston down, the oil can go through the hole, but it's viscous. It takes a while, and that's what dampens out your spring. And if you put this dash pot in the middle of a spring, you end up with a McPherson strut. So here's that picture of what's going on in the car body. And now I'm going to draw a true free body diagram showing what the forces are. Here's your car body up on top, and you've got a weight of that car body pressing down, which is mass times gravity. Mass of the car times gravity is constantly pushing it in a downwards direction. You've also got the spring. So if the car body is pushed up in the Y direction, then that spring is going to push it down. And how much is it going to push it down? It's going to push it by proportional to the K, proportional to Y. The higher up you pull the car, the more that spring is going to drag it down. And there's a spring proportionality constant called K. If it's a big, beefy spring, K will be big. If it's a little wimpy one, K will be small. This dash pot provides a force that's proportional to not how far it's been pushed, but how fast it's pushing. If you push the dash pot very, very slowly, it's not going to provide any resistance at all to motion. But if you push it really hard, it's going to provide a lot. And in fact, we can represent that pretty easily by the velocity, the derivative of its y value. So the derivative of its y value is how fast is it moving. And there's a constant of proportionality there too. It's traditionally called B. And then the only thing that would ever make it move then is the force of the road. So here in physics, if you've taken first semester physics, is your free body diagram of the car. And for a typical BMW, actual values are mass is about 1,500 kilograms. You just put it on a scale to measure, right? Or K is about 750 kilograms per meter of distension. So the way you'd measure that is you'd take the spring and you would measure how tall it is, and then you'd put a weight on it, maybe 100 kilograms, and it would displace. And if you divide the weight that you put on it by the amount that it displaced, that would be your 750. The typical dash pot coefficient is about 750 kilograms now per meter per second. So for every meter per second it's being pulled out, it resists that motion by about 750 kilograms. You could do the same thing. You'd put up a video camera, attach the weight to the dash pot, and let go, and it would slowly go down. With a video camera, you could see between two frames it moves 6 centimeters. You know how fast your video rate is, 25 frames per second, and you could divide back out. And then gravity is a constant, 9.8 meters per second. So this doesn't answer any of the marketing guy's questions. He's still completely confused and kind of overawed by your mathematical approach. Your approach is going to be to first find the differential equation that controls this car using a branch of mechanical engineering called statics. If you have time to take one course in engineering that's not electrical, statics is the class to take. What circuits is to electrical, statics is to mechanical. It's just the fundamental of all mechanical engineering. And I'll give an example of it today. It's actually a lot easier than you think, and it's very related to circuit analysis. You're going to take the Laplace transform of the differential equation. You're going to find, wow, that was poorly written. You're going to find the transfer function in the frequency domain. And then you'll look like a star to the marketing guys by answering all the questions. And it will really seem like magic. So let's do it. First, you're going to find the differential equation. Statics says that the sum of the forces in the vertical direction is equal to mass times acceleration. I guess that's actually dynamics, but it makes sense. The sum of the forces, if there's a leftover, if the thing isn't moving, it's going to be 0. And if it is moving, it's going to be mass times acceleration. So we can add up all the forces right here. In the positive direction, we've got the force of the road is acting in the positive direction. We'll subtract from it the dashpot force. We'll subtract from it the spring constant force. We'll subtract from it gravitational force, which is all pushing down, and all that has to end up equaling mass times acceleration. So, okay, we can divide through, let's subtract our F road here. So we are going to say minus F road, that gives us minus by prime minus ky, okay, minus mass times, remember gravity is really just, I'm sorry, I don't want to spend too much time going through the details, the algebraic solving this, but I will say that if you solve this for y's and recognize that acceleration is just a clever way of saying y prime prime. Plug in these numbers, you will end up getting this equation, y prime prime plus 2 y prime plus 2y equals your x of t, where we've redefined mg minus force of the road to be our input. So this is what statics will give you, is this equation. And there's your differential equation. And so now we're going to take our second step to do the Laplace transform of it. I don't expect you to be able to go from this to this with this class, but you would be able to do it easily if you took the statics class. So now let's apply your Laplace transform. Phil, what is the Laplace transform of a double derivative of y? Do you remember? I'll start you off. It's something times y of s. That's the transform of plain old y. But what do you have to do to it to get it to y prime prime?
You have to multiply it by
Yep.
like, what was that?
Yep. So far,
I
Right.
can't, but I can't remember what it is to multiply.
it's s squared.
That's correct, right? Because it's something to the n, right? Yeah.
That's right. Every s is like taking a derivative. So this would just be 2s y of s plus 2 y of s equals, and Phil, just to finish it up, how would you represent the Laplace transform of x of t, of a generic x of t? Given that we represented the generic transform of y of t as y of s.
It would just be like x of s, right? The capital
it.
X.
That's it. And so now we're going to find out what that Laplace transform is. So we'll take our y of s, our output, and we'll just factor out our y of s. We get s squared here plus 2s plus 2, and all that equals our x of s. So now, Sabine, tell me what our transfer function is, where we define our transfer function always as being our output divided by our input. So what is it for this particular vehicle?
We have s squared evaluates to e to the.
Oh, no, we're not. You're thinking time domain. We're still in the frequency domain. There's no t's here. What I want is, what we've done so far is we've gotten this is our differential equation. And now I want you to go, all right, so.
Did you just want me to divide then in
Yeah.
order to? Okay,
That's it.
so yeah, it would just be y of s over x of s equals that s squared plus 2s plus 2.
So are you saying that this is equal to s squared plus 2s plus
No,
2?
that's not true. That's not true.
It's close.
Would 1 over?
Bingo, that's it. That's it. So that's our transfer function. Now just realize what you've done. You've changed this physical car suspension system, this verb that changes an input signal of what forces you encounter on the road as you're driving, into an output signal of how your car body is moving. That verb that does that transformation, you've changed this into a single polynomial function in S. That's pretty wild. So that was your third step. And now here's the crazy part. So far, the marketing guys are looking at you like you've got 4 eyes. They're seeing you move around S's and derivatives, and they're saying, I don't see how you can answer my questions at all. But now you can directly. Answer the question, does it bounce when it hits a curb? Well, here's the answer. I don't care what kind of input you give it. If it's a curb, if it's an impulse, if it's a little ramp it's going over, if it's a pencil, whatever it is, your output, here's where we do the magic, is always going to be equal to h of s times your input. So it's always going to look like 1 over s squared plus 2s plus 2 times whatever your x of s stuff is, times x of s. But when you inverse transform that to find out what the car is doing, it's going to have roots from this. And Sabine was already graphing up our roots. Our roots for this one happens to be s plus 1 minus j, s minus 1 minus j times stuff to do with our x of s. So that means, I'm mixing up my notation here. So far, this was all y of s, but now I can finally determine what my y of t is. And that means it's going to be something, this part here, I can see those roots are going to give me something times an e to the minus t. That came from that root, times a cosine of t, that 1 times t, that part came from this root, plus some sort of angle. What that angle is and what that coefficient out here is depends upon how we do our partial fraction decomposition, plus stuff from whatever our x of t was. But we can directly answer the marketing guy without having to do any partial fraction decomposition, because our y of s will always have complex roots from our h of s, because our impulse response has complex roots, because our transfer function has complex roots. Our output in the time domain, in the frequency domain, will always have complex roots. And therefore, our output will always have this cosine term that will always decay. We can't get around it, whether or not we go over a impulse or a step or a pencil or anything, it's going to oscillate. And so just looking at that, we can say, yes, it's going to bounce on the curve. I can see that it's got complex roots. It's going to have to bounce. So then they say at what frequency? And you look at to find the frequency, you notice that S is always of the form a real part plus J times an imaginary part. And so looking at it, you can see your omega is 1. And so you say, well, you start to say omega equals 1 frequency, then you realize they don't know what omega is. So how do you convert that into something they understand? Dom, how would you convert omega equals 1 to something that they'll get?
So omega equals 1. So I'm not gonna lie, I just got back from the bathroom. I'm trying to think about I'm trying to think about it.
Frequency always equals omega
phase
over
shift.
2 pi. So since
Right.
omega is equal to 1, it's 1 over 2 pi, which is, well, it's about 1 over 6. Is that right? Yeah, that's right. So that
Okay,
they'll
I was-
understand. They'll still not understand 1/6 hertz, but they will understand every 6 seconds it's going to oscillate. That they'll get. So now, it's just like magic. You did all these numbers, and all of a sudden you can say, yeah, it's going to bounce. Yeah, the frequency is going to be about, it's going to, every 6 seconds. That's not too bad. How fast does it take to settle? John, how fast does it take to settle? This was this answer. This was this answer. And now, take a look at how fast does it take to settle? So what's its tau? What's its time constant? Way back from circuits 2. John Arger? Anger, I'm sorry. I'm so used to calling you guys by your first names, and now when we have first name conflicts. Oh, I just assumed, John, that your thing was pointed up too high, but maybe it's not. Connor, you tell me, what's the tau of this circuit?
Is it just 1?
Yeah, it's just 1. And so you know that it takes about how many time constants for a system to settle?
I don't know.
Do you remember that? Does anyone remember way back from circuits 2? How many time constants does it take a circuit to settle? You can see right from here in one time constant, it'll settle out to about e to the minus 1, right? When t is 1. And that's going to be about 0.3 something roughly. So it's going to be about 30% of its final value. But if we say it settles out when it's 1% of its final value, how many time constants is that? Anyone? It's been a long time. 5 time constants. And 5 time constants it settles. So that's going to be about 5 seconds it takes to settle. This is cool. This is like going from magic S's and things and all of a sudden being able to answer real world questions. Okay, so the guys from marketing think that you're like magic, but they're now going to play with you and they're going to say, oh yeah, hotshot, what would it be if you were on the moon? Would it still vibrate if we moved this thing to the moon? And so to find that answer, you would take a look at your original equation. And what would happen at moon is your G just would be a different constant. So your X would just be a different constant. Does that change what your H is to change your X? Nope, your H, your system transfer function is independent of your input. So your H doesn't change. So none of your analyses change. So you can confidently lean back in your chair and say, nope, on the moon, it'll still oscillate if it goes over a rock, and it'll still oscillate once every 6 seconds and dampen in about 5. The only difference in the moon would be that because this side would change, your numerator values would change, and so your amount of oscillation, your amplitude of oscillation would change, and possibly your phase angle too. Okay. I don't care if you can't duplicate all of that, but what I do care is that you see how powerful our signals and systems course is in fields that seem entirely unrelated to circuit analysis.
So is this specific to every suspension, or I mean, is this universal? I know that the equation and the way that we went about solving it is, but in terms of the numbers that we produced from the equation itself, that's for the BMW, but the 5 seconds and the 6 seconds, that's specific to the BMW.
That's
only.
right. If you put in
Okay.
different values of MKBG. But the point, though, is that the way that we analyzed it is true for any suspension system. But now instead of analyzing a suspension system, let's say we're interested in planetary thermal cycles as a function of being heated by the sun and also of our trapped greenhouse gas. You can do the same kind of analysis and just treat it as a different system, because once you get it, once you find once you find H, it doesn't matter if the input is thermal energy from the sun and the output is temperature, or if the input is distance traversed over a curb and the output is body motion, or if the input is the control of your joystick and your flight stick and the output is the position of the plane. It's all the same. It's an incredibly general tool. That should make you say, wow. You want to see if you can come up with a good model of how our country's GNP is controlled by government politics. You can quickly see, you can do an analysis like this and come to these conclusions. It's a very powerful method. Any other questions before I let you go?
So I have a quick question for step 2. So like I know that in DPQ, like
Yeah.
The Laplace transform of y double prime should be like something like s squared capital Y of sub s minus s y of 0, like the initial condition too. So are we
right.
not considering?
Right, that's right. And in fact, in this class too. So what Ben is saying is that if you take a look at our sheet for Laplace transforms, let me take a quick look to open that up. Yeah, I like the way that you're that you're thinking about this, Ben. Okay, so here's our transform sheet. And what Ben is saying is when you take the, shoot. Well, I don't know, I can't draw on this, but when you take this differentiation here, not only is a single derivative like multiplying by s, but you also get this extra constant term out there, which is what your function is doing at time equals 0 minus. And if you're taking a double derivative, yes, there's the x squared, but there's also these extra terms that are related to your initial conditions. And so all of this, remember, has to assume what your car is doing before time equals 0. And so we're assuming that our car is driving flat before time equals 0. It hasn't just hit one curb and now it's hitting another curb, that it's been flat and then it hits the first curb. So we're assuming all of our initial conditions are 0 to do this. That's correct. And I did kind of hand wave over that, but I think it's clear when marketing is talking about it, they're saying, is it going to vibrate because it's gone over the curve, not is it going to vibrate because it was already vibrating before when we started to look at it. Is that clear, Ben?
Oh, yes, sir. Okay, thank you, sir.
Yeah. So to do the actual analysis correctly, you'd have to know, to find out the full output of the car, you'd have to know what the initial conditions were on the car. What was happening to it just before you started doing the analysis, before time equals 0. Yep, that's true. Any others? Okay, I will see you all on, oh dear Lord.
Tuesday.
No, I just,
Thursday.
no, we're going to see each other on Thursday because Tuesday's class is not here. But my dear Lord, I really hope that I began recording this before I started talking.
We're not gonna have class on Tuesday?
That's correct. All classes for all VMI, everything on Tuesday is canceled.
Oh.
And it was planned to be that at the very beginning of the year. You can see it if you take a look at our Canvas class. It's because of the symposium, and that's been planned out a year ago. I think that's been planned out a long time. All your classes on Tuesday are canceled. Okay.